Okay, so for the circular motion, what is the meaning of the circular motion? So the equations that we have already, you could say, discussed, for example, the final velocity is equal to initial velocity plus at. So this is the first equation of the motion. And here, this equation of the motion is mainly defining the linear equation. Okay. And so this is, you can say, for the one-dimensional motion. But here, what we do have, we have an object which is moving in the circular path, and that actually motion of this object, you can actually say that this is actually a circular motion. And here, when this object will be moving, then we can define its velocity vector, that will be just a straight line, and this velocity vector will be like this. And this velocity vector in this way, for example, now at some other time, this object moved to the new position, and then this object's velocity vector will be like this, then means that you can say it will be always the tangent at the point where the object is, along this circular trajectory. Okay, now we can actually say that an object uh, moves uh, in circular motion with constant speed, with constant speed. And if the speed is constant, then it is not necessary that the velocity is also constant. So velocity is not constant. Why velocity is not constant? It is accelerating. Yes. So why? Because the direction is continuously changing. Direction is continuously changing. Okay. So direction is continuously changing. So in this circular motion, when we actually defining this circular motion here, this vector is in fact the linear part, isn't it? The linear part. However, this object is moving here along this path. And then now our next task is to develop a relation between linear and angular motion. For an example, we consider that this object, it was at some position here at time t is equal to 0, and then after some time t, this object actually moved at a new position at the time t is equal to t, and for this motion it actually revolves an angle, and that angle is theta. Now you see that when we are defining the circular motion, and then what we will define rotation. And the rotation is mainly defined with this angle. Okay, now let me draw this triangle like situation. So we have this situation, and here we do have this almost curved path. So this is a position number one, position number two, and here it is the center. So we have here, this is a radial vector, and here this is also radial vector. For a very small angle theta, if this theta angle is small, then we can actually find that this thingy, this linear path and this curved path are almost equal to each other. And this linear path, we can say this is actually the linear displacement ds. Okay, linear displacement ds when this angle is also infinitesimally small, meaning that this is d theta. And then according to this triangle, which is isosceles triangle rule, that this ds, which is actually this part here, that no, ds is the linear part. Ds is the linear part, is the straight line. So because that, for example, that now if we say that this triangle is like this, and this is a curved path, and then this angle is a theta, and this is a curved path, a sector, and when we will consider a very, very small angle, so this angle is, for example, just d theta, then you can say this is just a straight line. This is just a straight line, and that you can consider it is a delta S. And now this triangle is a isosceles triangle because this side is the radius and this side is also the radius, isn't it? And then this ds, that will be equal to ds is equal to r, which is the radial vector, times d theta, sorry, d theta, which is the angle. So now here in this equation, what is this ds? So ds is the linear displacement. It is the linear displacement. Okay, linear displacement. Okay, and this radial vector, we can say, is a radius of circle, of a circular path, of a circular path of the motion. And then this d theta is a angular displacement, is a angular displacement. Okay, and this angular displacement, and here is a linear displacement, that it tells that this linear motion can be related with the angular motion by just multiplying with this r vector, which is the radius of the radial path, circular path of the motion. Now we also know that actually the rate of change, the rate of change of displacement. What is it? Rate of change of displacement. Mhm. Rate of change of displacement is velocity, isn't it? Yes. Okay. If this is the velocity, then we actually differentiate this equation with respect to time. Then we will get that ds divided by dt, meaning though it's a first order derivative of displacement, and then this is going to be r and d theta over dt. Okay, and one thing which is, this is the differential equation here, and this differential equation you can also actually integrate it, and you can say that the linear displacement is equal to the r times angular displacement theta. Sorry. Yes, because r is constant. R is a constant. So if this is constant, then it will be just as it is, isn't it? Because this is a constant radius of the circle. When this object is moving in the circle, it is not changing its radius, that what we have considered for the simple circular motion. Okay, so in that case, here in this equation, when we are differentiating it, so it is going to be the linear velocity, because this is the rate of change of the linear displacement, and here we said this theta is our angular displacement. So then the first order time derivative, the time derivative will tells us the rate of change. Okay, and that will be the angular velocity. So the linear velocity is equal to r and omega. So this omega is angular velocity, angular velocity. Okay, so let's actually define first here. We actually learn two equations, that S is equal to R theta, and these are actually you can say the displacement equation. And now we have a velocity equation, that V is equal to R omega. Okay, if this is V is equal to R omega, then here the units of linear velocity, we know these are meter per second. What about angular velocity? And angular velocity, we already actually defined that it is actually the velocity of an object when it is moving in a circular path. Okay, it's having a rotation. Then this rotation, we said that the rotational or the angular displacement is this angle theta, and that will be measured in radians. That will be measured in radians. So the units of angular displacement are radians. So in the same way, the units of angular velocity will be radians per second, isn't it? Yes, very good. So now, again, if for example we take the time derivative of this velocity equation, then we will get the derivative with respect to time of velocity, meaning that it will tell us the rate of change of velocity, isn't it? And that is going to be r times d omega over dt, because r we are considering here again the constant. So then we have acceleration. Rate of change of velocity is acceleration, and this acceleration a is equal to r times alpha. R times alpha, and alpha is again this angular acceleration, is angular acceleration. Okay, understand? Very good. Angular acceleration. Okay, so now I have a question about the circular motion. We know that, for example, the earth is revolving around sun. Why earth is revolving around sun? Because of the gravitational force between sun and earth. So meaning that the sun is actually pulling the earth toward itself. So then we can say that this is actually the force of this gravitational force between these two objects. And this gravitational force is in fact forcing this object in the circular motion. And that force, the force which keeps that force, the gravitational force, is providing the, is, you can say, is forcing the object to move in the circular motion. That kind of a force, we call it a centripetal force. A centripetal force. And the centripetal force is the force which actually forces the object to move in circular motion. And this force F is Fc, we call it, is equal to mv square over r. What is this r? R, thank you. R is the radius. R is the radius of this circular path. For example, in this our example of sun and the earth, so we can say this r is distance between sun and earth, isn't it? And earth. Very good. So now from this equation, we know what is the relation of this linear velocity with the angular velocity. So you can also find this centripetal force in the angular, you can say the terms m divided by r. M is the mass of the object. So in this case, this will be the mass of the earth. And v is equal to r omega. So then it will be r square omega square. And this square will be cancelled out this one, and we will get the centripetal force m r omega square. Okay. And then we also learn by the third law of motion. What was the third law of motion? Yes, it means that if we have a centripetal force which is forcing the objects to move in circular path, that must be equal to a force which is actually trying to kick away the object from the circular path. So for example, if this link that is provided through this gravitational force will be broken, then this object, this earth, will actually lose the connection with the sun, and then it will fly away. And at that time, the centrifugal force. We call it centrifugal force, and this centrifugal force will actually, you can say, kick it out from its orbit. So it will go to a linear motion away from the sun, isn't it? So the centripetal force and centripetal force, they are equal in magnitude, but they are opposite in direction. So that's why we have here negative sign. Okay, understand? Okay, very good. Any questions so far? Okay, so now I'm going to solve these equations of the circular motion little further. In this, actually, the centripetal force, that we say that mv square over r. R is distance between the center and the object, meaning that the radius of actually the circular path. If that actually, you can say the force is coming from the gravity, then we can say that in that case, that will be G, the capital G is the constant, gravitational constant, and capital M, let's say this is the mass of sun. This is a mass of sun. So in that case, and then small m, and that is the mass of earth, because mass of earth here, because earth is revolving around sun, that we actually considered in this situation, and then we will have r square, isn't it? Yes, and here you can actually cancel out these small m's, and this radius will cancel this square, and we got r v square is equal to the gravitational constant, mass of sun, and divided by the distance between sun and earth. So the velocity of earth v is equal to g times capital M divided by r and its square root. Okay, so what kind of this velocity is, Motsam? Hmm? Hmm? This is the velocity of what? Hmm? This is the, yes, this is the velocity of Earth. Very good. So then, does it mean that using these, you can say that these kind of relations, we can find the velocity of any, you can say, the satellite that is actually at some distance from Earth? So, for example, if we want to find the velocity of the moon, then you can simply say that in that case, this mass will be the mass of Earth, isn't it? Mass of Earth. So if this is the mass of Earth, then this will be the distance between Earth and Moon, isn't it? And Moon. So from this equation, because G is always constant, this is a universal constant. So that is equal to 6.67 into 10 raised to power minus 11 Newton meter square per kilogram square. Okay, so now here the learning point is that when you are firing a satellite, actually this is Earth, very strange Earth, global warming. So you are firing a satellite and you want actually to put it in somewhere in this actually the you can say the orbit, and we know that what is the distance of this actually the orbit from the Earth. So then this distance plus re, the radius of the Earth, that will be the total distance that we are using here in this equation, and it will actually give you the value of the velocity, that what will be the velocity of the Earth. Now, if, for example, that you say that you have Earth, and you actually put a satellite which is moving around this Earth, what it actually keeping its position always at one particular position above the Earth, then we call them that these are geostationary stationary satellite. Okay, satellites. Okay, so geostationary means that they actually always keep their position at one particular place above the Earth. So in that case, it means that their angular velocity, we would know that because we know that in 24 hours, Earth completes one revolution, isn't it? 2 pi, isn't it? In 24 hours, it actually completes its one rotation. So this is actually the time. This is the time. And then we can actually calculate its position in this r, that how far it should be. Okay, how far it should be using this information and using this formula, and then we can estimate that where our satellite must be if we will throw, or if we will, you can say, push, or you can say fire this object at that place, then we can find our you can say the velocity of the object. Okay, understand? So here I have uh, one actually the question, if you can try. So can you calculate speed of Earth, Earth around the sun? So here, as I already give you the value of the g, then which mass you need, mass of Earth or mass of sun? Mass of sun, because here we said that when we are going to measure the speed of Earth, sorry, speed of moon around Earth, then it will be the mass of Earth. So we said this is the mass of moon, because moon is, sorry, mass of Earth, because Earth is revolving around sun, isn't it? So that was cancelled out. So mass of the satellite doesn't depend, it depends on the distance between the objects, isn't it? So here the mass of sun is 2 times 10 raised to power 30 kilogram. Okay, and the distance between Earth and sun is 150 into 10 raised to power 9 meters. Okay, can you calculate now?